Sure. So you got a problem number? Which section? 3.4. 3.4. All right, 3.4, which number? It's only 4 questions. Are you in the supplemental questions?
Yeah, I can do this question on half.
So there's 3-4 supplemental. Okay. D arrow A and C. So all of this gives B? Okay. So like that. I'm just going to leave the lights off. I'm in a mood. So A implies B, C implies B, D implies A and C, therefore, and D, and all of that together implies B. So let's write this in our usual sort of calculation format. A implies B, C implies B, D implies A and C, D, therefore B. So this is what we're asked to prove. So let's look at a direct proof. So let's start off with, so you got any thoughts on this? Like what's going to go together with each other in here in a way that's going to possibly help us? We're trying to prove B in the end. There's only 2 things we're given that lead to B. That's those first 2 statements. And so if we could prove A was true, for example, that would give us B. Or we could prove that C is true, and that would give us B. And there's only one statement that leads to A or leads to C, and that's this 3rd statement. And this requires D, which is the 4th statement. So the chain of thinking that I've got in my brain right now is if we know D, that will give us A and C. And if we know A and C are true, we know A is true. And if we know A is true, that'll give us B. So we can piece that together. Step 1 is D, that's a premise. Step 2 is that D implies A and C. That's also a premise. Step 3, A and C, that's direct reasoning, right? If D, then A and C, and we're told D, and therefore A and C. So that's direct reasoning. And I don't remember what the name of the rule is, but if you know A and C is true, you also know A. There's probably some fancy name, but I'm just going to say definition of and. But I think it's conjunctive simplification, maybe. And we're also told if A, then B. And that's a premise. And so this was direct reasoning of 1 and 2. And so we can put 4 and 5 together and conclude B. That's direct reasoning. Of 4 and 5. And so there's a direct proof of B given those premises. An indirect proof would start off by assuming not B. So this is our this is the negation of, I don't think negation of conclusion is official technical speak. It's assuming the opposite of what we're trying to show, right? The negation of it. So we're assuming not B, so this is an assumption. What does not B get us? All right, so B, not B together with A implies B, which is a premise, gets us not A. That's indirect reasoning. And it also gets us not C because we're told C gives us B. That's a premise. And we have not B, so we also have not C, and that's indirect reasoning of 3 and 4. So we're told that we have not A and not C. So we're trying to find a contradiction, right? And our contradiction is going to be, we're going to show that A and C is false. And do we have to do De Morgan in here? We actually don't. We didn't have to do this at all. In fact, our fourth step could have been not A or not C. Because if we know that this is true, then certainly when we OR with something else, it's still true. And then De Morgan's theorem tells us that not A or not C is the same thing as not A and C. Right? So this is certainly true because of De Morgan's theorem. And then we can use our third premise, D implies A and C, which tells us not D, and that's indirect reasoning. But we're also told D, which is a premise. And so there's our contradiction. So this assumption led to a contradiction, therefore that premise must be false, so its complement must be true, which means that B is true. So direct, you use the premises that you're given and you use the rules of inference and you try to get to the conclusion. Indirect, you assume the negation of what you're trying to prove and you use your premises and your rules of inference and you try to get to a contradiction. And really what we're showing is that not B implies false, right? Because here we've shown D and we've shown not D, and that's false. So not B implies false, which means true implies B, therefore B. Other questions? Yeah, those would be good to have in your note card. And it's not that I'm super worried about knowing the exact right names for them, but you want to make sure that what you're doing from one step to the next is one of those basic rules. And if you don't write them down, you might combine 2 or 3 of them into a single step, and that loses points. Okay, what should we prove? Okay. So the sum of consecutive squares is this crazy formula, n plus 1, 2n plus 1 over 6. This is what we want to prove. All right, what's the first step in doing an inductive proof?
Well, I said let P of K be the proposition.
Good. So let P of K be the proposition. What's the proposition?
Oh, it was, I just switched the n for K.
Okay, good. All right, does that look like a good proposition? Should I say for all k bigger than or equal to 1?
Oh, yeah, that was actually given too, so probably.
Probably not, though.
No.
Because P of k is a statement that this is true for k, right? Saying this for all k bigger than or equal to 1, that's a proposition that has nothing to do with a particular value of k. That's what we want to prove. We want to prove that this is true for all n bigger than or equal to 1. In other words, we want to prove P of k for all k bigger than or equal to 1. But P of k itself is usually not going to be some statement about k for all k bigger than or equal to 1, right? P of k is just a particular proposition. P of 5 says the sum of the first 5 squares is equal to 5 times 6 times 11 divided by 6, right? But we don't usually put that quantifier on the statement of P of k, but it does go on the statement of what it is that we're trying to prove, which is that P of k is true for all k. All right, we've got a good proposition. What's the next step? P of 1. So P of 1 says 1 squared equals 1 times 2 times 3 over 6, which is equal to 1. Is that true? Is 1 squared equal to 1? Yes. So we have a base case. All right, what's our next step?
I said assuming that P of K is true.
Okay. Suppose P of k is true. What do we want to do? We want to prove P of k plus 1. This is a much easier task than this. this thing we're after for the problem says prove P of k is true for all k. That's a hard thing to do. All we're trying to do here is say if P of k is true, let's just prove this one other proposition is true. Right? We're given one, we're just trying to prove one more. But together with mathematical induction, that'll prove an infinite number of these P of k's is true, in fact, all of them. All right, so now we know what we're trying to do. So P of k is true. That's an assumption. So what does P of k say? Yeah, let me write it like that. So definition of P of k says 1 squared plus 2 squared plus up to k squared equals k times k plus 1 times 2k plus 1 over 6. All right, where do we go from here? Okay, let's make an ignore section. What are we hoping to eventually show? Yes, we want to show P of k plus 1, which says 1 squared plus 2 squared plus k squared plus k plus 1 squared equals, and we want it to end up being k plus 1 times k plus 2 times 2 times k plus 1 all divided by 6. But it's this part that we can turn this into pretty easily, right? If we just add k plus 1 squared to this side, this is going to look exactly like this. This is not going to look anything like this, but that's okay, right? We're going to work with that. But let's just add k plus 1 squared to both sides. Right? And if that previous line is true, this line's certainly true because I added the same thing to both sides. So this is just algebra. But now we want to somehow work this using more algebra and have it end up looking like this thing that we're after. And I don't know how to do this. What are you substituting?
K squared for the original thing that we had, which was k times k plus 1 times 2k plus 1 over 6.
So you're substituting.
We already know that k squared is equal to that.
If we substitute this in for this,
No, not that. What we had up originally at the very top.
up here.
Yeah, except with k's instead of n for k squared.
Mm-hmm.
Because then we essentially have the same thing on both sides. And we know that's true, right?
Yeah, but that hasn't gotten us to showing that this is equal to this.
Then we just stand up.
You're going to have to somehow show that this is equal to this, ultimately. And the only thing we can substitute in from the beginning would be 1 plus 2 plus k squared, right? And that's just going to show that this is equal to itself. And that's true, but we haven't done anything to show that this is equal to that. But let's try combining and simplifying and doing those things we do. Say again? That 6 makes it difficult. Let's multiply this k plus 1 squared by 6 and see if we can get lucky. So this right-hand side is equal to k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared, all divided by 6. All right, which is equal to k times k plus 1. I'm going to get rid of this. Times 2k plus 1 plus 6 times k squared plus 2k plus 1, all divided by 6. I think we could get fancy. I think we could have factored out a k plus 1 from both of these. Maybe that's not a bad thing to do. Let's do that. Let's take this k plus 1 and one of these k plus 1s and pull it out. So this is k times 2k plus 1 plus 6 times k plus 1, all divided by 6. And I'm cheating. I'm using my ignore area. I know I want a 6 on the bottom. Well, I've got that. I also want a k plus 1 multiplied by some stuff. Well, now I've got a k plus 1 multiplied by some stuff. And I'm avoiding getting cubes where if I just multiply this out, I'm going to have a k cubed in there. And that's going to cause me some pain and suffering. So let me just simplify the stuff in the brackets. So this is 2k squared plus k plus 6k plus 6, all divided by 6. So we have k plus 1. Thing in the brackets is now 2k squared. K plus 6k is plus 7k plus 6, all divided by 6. And if we could factor this thing in brackets, we might get lucky, but I'm going to cheat at my cheat sheet and see what I'm trying to turn it into, which is k plus 2 times 2k plus 3. So if I do k plus 2 and 2k plus 3, what does this turn out to be? 2k squared plus 4k plus 3k is plus 7k plus 6. That's perfect. And I didn't use my cheat sheet. I'm just a genius, right? I just knew how to factor this. No one can argue with that because you can see that this is equal to that. But you use your cheat sheet, right, to help you figure out what steps are going to get you progress. All right, so now we've shown that this thing that started on the left of this, the sum up to k plus 1 squared, is equal to k plus 1 times k plus 2 times 2k plus 3 over 6. And now we're just going to write this in a slightly different form. K plus 1 times k plus 2. And instead of 2k plus 3, I'm going to write 2 times k plus 1 plus 1. Because that's 2k plus 2 plus 1 more, all divided by 6. And that's exactly what P of k plus 1 says. Right? P of k is the proposition that your sum up to k gives you this. P of k plus 1 says a sum up to k plus 1 squared gives you k plus 1 times k plus 2 times 2 k plus 1 divided by 6. That's exactly what we got. So therefore, P of k plus 1 is true, and therefore P of k for all k bigger than or equal to 1. Yes, so if you had to prove this for all k, positive and negative, one approach would be to make a pair of propositions, right? One that works with k and one that works with negative k. right? And then you could take k, your first proposition from k equals 1 on up, and your second proposition from k equals 1 on up would be doing the negatives, basically. You can technically do mathematical induction going down also, but we just don't normally do it that way. Up later. All right, other questions?
I was working on one more problem where it said, like, prove every integer has a bigger integer than that.
Every teacher has a what?
Every integer has a bigger integer than that.
Okay. So prove for all n in Z, there exists a k such that k is bigger than n. K also contained in Z. What do we think about this? Given any integer, prove that there's an integer bigger than that. You could do induction. Right. So if we did this inductively, P of n would be the proposition that for any integer less than or equal to n, there's an integer bigger than it.
I was just thinking like the proposition would be an integer n exists. That's not a proposition.
So
I'm thinking if you can prove that integer n, then you can prove integer n plus 1.
yeah.
Something like that.
So with these kinds of questions, it's not always clear exactly how specific and detailed they want you to be. Like, are we allowed to assume certain properties of integers here? But here's a proof where we have to assume a few things. So let n be any integer. When we know that 1 is bigger than 0, because we just know that. And we know that if something is bigger than something else, we can add the same thing to both sides and preserve that equality, or that inequality. So n plus 1 is bigger than n plus 0. And n plus 0 is equal to n. And n plus 1 is an integer. Well, how do we know that? Because n was an integer, and 1 is an integer, and the integers are what we call closed over addition. Means if you take two integers and add them, you get another integer. So the reason for this might be closure of integers under addition, and 1 is an integer, or it might be common sense, or I don't know what. Like I say, it depends how detailed they're asking you to be. But here we've shown that n plus 1 is bigger than n, and it's an integer. That's all we needed to do. So that's a proof by demonstrating a specific example of what you're asked to prove. That's sometimes the easiest way to prove something. If you can actually find a formula to produce one of the things you're asked to show exists, then that certainly proves existence.
So here's a good example of what I was asking earlier. Really, all you've done is proven that integers greater than 0 have to be created. Obviously, that just translates to 1. But if you wanted to do just as easily n minus 1 is greater than, or n plus 0 is greater than n minus 1,
Mm-hmm.
which is good.
Yeah, so I made no assumption that n was positive here. So in this case, n could have been any integer, positive, negative, right? But I understand what you're saying.
Because your base case is,
I don't have a base case because I'm not really inducting here. I said let n be any integer, and I've shown n plus 1 is bigger than n.
the 1 is greater than 0. Then why do you need that then? Couldn't you just not say 1 is greater than 0?
Well, then how would I get an integer bigger than n?
By adding 1?
But how do I know that n plus 1 is bigger than n? maybe it's common knowledge, but this puts a little more detail on there. If we believe that 1 is bigger than 0, and we believe that this property of inequalities is preserved under addition, then we've proven that n plus 1 is bigger than n. But we might have just said, you know, n plus 1 is bigger than n, because that's common knowledge. But on this kind of question, like I say, it's not clear how much common knowledge you're supposed to be assuming. So how much can we take for granted with common knowledge? I heard you make a comment the other day, Pearson, about 1 plus 1 equals 2. And how with some of these simple statements, the simpler they are, the harder they are to prove, right? And that's really true. Yeah, so we start with axioms, right? So geometry starts with 12 or 13 axioms. Set theory starts with a set of axioms, and we build from there. But there's these problems, right? If we started with set theory in a naive setting where we just set a set as a collection of objects, we get to paradoxes like Russell's paradox. In the 20s and 30s, two mathematicians, Whitehead and Russell, set about trying to do a systematic development of arithmetic that would be completely rigorous and devoid of paradoxes and would let you prove or disprove any possible theorem. And they developed a language for doing this, and they published 2 volumes called Principia Mathematica. And it's available from Amazon, but it's also freely available elsewhere. So this was first edition, 1910. I didn't know it was that far back. But let's get into the good stuff. So there's some of their alphabetical list of propositions referred to by name. So these are propositions and the names of them. And this is all some kind of language they developed. But let's just jump into the guts of it here. So this is what the whole book looks like. It's just all these statements that kind of look like all the same, right? But they're developing arithmetic. I don't know who proofread this for typos. But all of this means something, right? And this is all, big, long derivation. Everything comes from the previous things. And these things with numbers 11, 24, that's a theorem, and then DEM is a demonstration of it. And they come down to proving that, yeah. And so this is all built on top of everything else. And it just goes on and on and on. There's some words in here, but it's mostly just these proofs. And this is 2 volumes. So volume 1 is 719 pages, and volume 2 is about as big. Yeah. And where does this get us? So over here on page 379, right, 400 pages into this, they have some more theorems, and at the end, they make the statement that from this proposition, it will follow when arithmetical addition has been defined that 1 plus 1 equals 2. So there's your answer. It takes 379 pages of this stuff to lay the foundation for proving that 1 plus 1 equals 2. So these things that we take for granted, right, 1 is bigger than 0, or an integer plus 1 is an integer, right, depending on where you start from, can take a lot of work to get to.
Are they saying that A exists with a set of 2? I guess that's...
I don't know what the symbology is here.
No,
I've never dug very far into it, but people apparently still buy this from Amazon and read it. Maybe on bets or something, I don't know. But I'm happy that this exists because it looks like stuff that I've done in the past, and I've sat back and wondered, why the heck am I doing this? I must be insane. But at least I'm not alone, because other people have done far crazier things. So that's encouraging. The real bummer was that a few years after this came out, Kurt Gödel came along and showed that you can't do this. You can't have a complete definition of an arithmetic system that does not have contradictions or incompleteness. and it kind of blew a hole in the whole master plan of making everything rigorous and derivable from first principles.
You're saying it was incomplete then?
I don't know how that reconciles with incompleteness.
I understand what the contradictions mean. That's ambiguous with our system. But what's it mean to be incomplete?
To be incomplete means there's a theorem that can neither be proven nor disproven,
Oh, okay.
which to me I think of as its truth value has no impact on anything else. Right? It might be true, it might be false, but the truth or non-truth of this statement cannot affect anything. If it could affect something, there'd be a way to prove or disprove it. If you could find a counterexample, that would disprove it, right? But there cannot be a counterexample. But does that prove it? Not necessarily, right? If you could prove it, then it would be affecting some other part of your system. So this gets into a whole debate that we used to have around this topic of purple aliens, right? And there's a purple alien standing right next to me, but you can't see it, you can't touch it, you can't interact with it, it has no effect on anything, it can't move anything in our universe. It has absolutely no impact on any piece of our existence. Is it possible that it still exists, though? Right? So it's this third state of being, existence, non-existence, or existence, but in some sense doesn't matter to our universe. And that's kind of where incompleteness figures in for me, right? There might be a purple Sasquatch standing right here next to me, there might not be. But if it's completely invisible, everything passes through it without interference and so on and so forth, right? Neither its existence nor its lack of existence has any impact on our universe. There's no experiment we can conceive of to prove or disprove that it exists. That will not be on the test. All right. Others? So we've got about 5 minutes left. So let me run through an example from RSA. And tomorrow will be the midterm. Monday we'll start combinations and permutations. But I spun out some specific examples using RSA. So let me just show you what this looks like. So I'm going to pick, for example, P equals 17 and Q equals 23. And so their product, N, is going to be 391. So I can't use a very long message, but I could use basically any number smaller than 391 to be my message. So if I look at P minus 1 times Q minus 1, that's 16 times 22, that's 352. And this is also 2 to the 4th times 2 times 11. So when I want to find my encryption key, which is going to be relatively prime to 352, I just need something that's not divisible by 2 or 11. So I just chose an encryption key of 13. So that's my encryption key. So I'm going to take my message and raise it to the 13th and reduce it modulo 391. That's going to be how I encrypt. And to decrypt, I want a D such that D times E is congruent to 1 modulo 352. And the fact that E is relatively prime to 352 guarantees that I have such a D. And to find this, well, if two numbers are relatively prime, their greatest common divisor is 1. So I can try to find the greatest common divisor of 352 and 13. And this will turn out 352 equals 27 times 13 plus 1. And you might have to do more steps, but we got lucky here. So 352 minus 27 times 13 is equal to 1. And this is mod 352. 352 is just 0. Minus 27 times 13 is congruent to 1. Minus 27 is also 352 minus 27. So this is 325. So this is my decryption key, is 325. And if we take our ciphertext and raise it to the D and reduce it modulo 391, that should get us back to our plain text. So let's do our calculations. So for my message, let's suppose we pick a message of 234. So I want to do 234 to the 13th mod 391. So 234 raised to the 13th is that big long number. And if I reduce it mod 391, I find a ciphertext of 200. So my message was 234 and my ciphertext was 200. To decrypt it, I should take 200, raise it to the 325th, mod 391. So if I take 200 raised to the 325th, that's that big long number. If I reduce that modulo 391, there's my original message, 234.
So 13 is your key, your private key, and 231 is the public one?
Other way around, but it should be symmetric. So E is the encryption key, that's the public key, that's 13, that's how you code the message. D is the private key, that's how you decode.
And then the 391 is just implementation.
And 391 is part of the key. So the actual encryption key is 13, 391. So take your message, raise to the 13, reduce mod 391, that's your ciphertext. Okay, so the whole world knows this. They can take their message, code it up. Here's the ciphertext. You can't decrypt this unless you know this magic 325. And to find that, I needed to know what my original primes were. Right? Because my original primes let me figure out what P minus 1 and Q minus 1 was, which was my 352. And let me find my inverse of E. So the mechanics of doing this is very straightforward, right? This is all figuring out your decryption key based on your encryption key. But then to encrypt, you basically raise your message to a power, mod 391. To decrypt, you raise your ciphertext to a power, mod 391, and it brings you back to your message. And you can do this for any number smaller than 391, whatever your message might be, and this will reverse the encryption. All right, so assuming the roads are not sketchy tomorrow, we will have our midterm. But if it starts to get sketchy later on in the day, I may just go ahead and postpone it to Monday. But I will post a message on Canvas if I decide to do that. And if it's not getting sketchy, but it turns out tomorrow is totally dicey, right, I may just go ahead and postpone it. So stay tuned. It looks like most people made it here today.